Okay, finally we will be able to actually prove this statement, which we have seen many times, that pi1 of s1 comma 1 is z. But along the way we have done a lot of our technical work that we need, and things are going to be quite easy. Okay, so let's start. Let's define a function capital Phi from the loop space omega of s1 1 to z. Not maps to z, but to z. Okay. So suppose we are given alpha here. Okay. So what we'll do is let alpha tilde, and I'll keep using this notation. So this is going to be a map from 0, 1 to r. Okay, of course we are going to be using r to s1, the covering all the time. Be the lift of alpha with alpha tilde of 0 equals 0. Okay, there are many lifts, one for each integer in fact, because the initial point is an integer. But we are going to take the unique lift with alpha tilde of 0, 0. I'm reserving this tilde notation for that. And you just define capital Phi of alpha is alpha tilde of 1, where this lift ends. Okay, this was what we had done with our picture many times. We look at how it winds around and see where the end point is. When we start at the origin, the end point is going to be an integer. By the way, so this belongs to P inverse, not pi inverse, but the projection inverse of 1, which is z. So indeed it is an integer. We don't yet know about the group structure, but at least as a set, we are at an integer. Okay, so this so far so good. Okay, but now we want to define the same result, the function actually on pi1. So if alpha is equivalent to beta, that is to say alpha is homotopy fixing base points to beta, then phi of alpha is equal to phi of beta. This will let us define an induced map. Okay, so the proof is let H be a homotopy from the first chap alpha to beta and fixing the endpoints. Okay, and then let H tilde be its lift. Well, I have to specify the starting point, and of course that is H tilde of 0, 0 is going to be equal to 0. This is in real numbers. Okay, and now here is the claim. We'll be using similar arguments many times. So the claim here is that H tilde is a homotopy from alpha tilde to beta tilde. Of course, fixing endpoints. Fixing endpoints we already saw, because we saw the lift of a homotopy that fixes endpoints. How do we know it is from alpha tilde to beta tilde? So the proof of the claim is the following, that if I look at S mapping to H tilde of S comma 0, okay, now this is a lift, because we restrict a lift, it's a lift by the definition of S mapping to H of S0, which is alpha of S, and it's a lift of this, and with H tilde of 0, 0 equals 0. Hence, by uniqueness. So it is a lift, hence it is the lift. Hence by uniqueness, S mapping to H tilde of S0 is just alpha tilde. Okay, that is H tilde of S with time 0 is alpha tilde of S for all S in 0, 1. So we look at the homotopy. The picture here is that we are looking at H tilde and we are restricting it here. So we restrict it here. And that of course projects to the homotopy downstairs. And we can restrict. And if we restrict here, we get alpha. And so this restriction is the lift of alpha. And the starting point is the correct one. So by the uniqueness of lifts with given starting point, this must be alpha tilde. And of course, similarly, we get h tilde of S1 is beta tilde of S for all S in 0, 1. Namely, if I look at the lift restricted to the top, then that ends up being so this restriction is beta, hence this is a lift of beta, and hence must be beta tilde. So we have in fact a homotopy between alpha tilde and beta tilde. Okay, that leaves us in good shape. So what we know is alpha tilde and beta tilde are homotopic fixing endpoints. Now we saw that if hence alpha tilde is homotopic fixing endpoints to beta tilde, this implies that alpha tilde of 1 is beta tilde of 1. Same with 0, but that was by construction. But remember, this is phi of alpha. And this guy here is phi of beta. So this concludes our lemma. Okay, so thus we can pass to the quotient. Phi induces phi, which maps pi 1 of S11. Remember, this is omega of S11 by the same equivalence relation we are considering to Z. Okay, so far so good. This is our homomorphism. What we have to show now is that it is injective. Sorry, this is our map. So far we just know it's a function. We have to show three things. Phi is a homomorphism. Phi is injective. And phi is surjective. Okay, of this the most work will come from homomorphism. So let's just do that, and then we will in the next segment look at injectivity and surjectivity. So let's look at this homomorphism property. Okay, so let's pick two elements, alpha, beta. They are in omega of S11. Okay, and so that means that their equivalence classes alpha, beta belong to pi 1 of S11. Okay, I think up here I was a little bit no, I didn't use alpha there. So it's a map on equivalence classes, and so we are looking at phi of alpha and times phi of beta. Okay, so alpha tilde, beta tilde as before. So now I'm going to construct a lift of alpha tilde and beta tilde. Alpha star, and so we construct the lift of alpha star beta starting at 0. Now you might naively think that it's alpha tilde star beta tilde, but it's not, because alpha tilde begins and ends somewhere, and then beta tilde again begins at the origin. Okay, so this is roughly how they look. Maybe alpha tilde went up to, maybe this was alpha tilde which went from 0 to 2. Okay, and beta tilde went from 0 to 1, for example. Remember, there are paths that end at integers. So it's kind of clear. Let me actually color these. Let's redo this part in color. Exactly the. Oh. Okay, so let's make alpha tilde as this purple color, and maybe beta tilde is blue, and it ends here at 1. Of course, these don't wiggle. The wiggle is colorful just to make things very vivid, but so this may end at 1 and this may end at 2. They are along the real line, but you won't see them. So this is, suppose this is alpha tilde and this is beta tilde. Now how will I construct a lift? It's not by taking alpha tilde followed by beta tilde, but instead we will translate this guy. So I'll take beta tilde and shift it to start here and end here. And it's easy to see that this will indeed end at 3, which is the sum. And indeed, so let's define a function I'll call it eta tilde because alpha star beta tilde has already been defined. We'll claim that it's equal to that. So this is going to be alpha of 2s if, alpha tilde of 2s if 0 is less than or equal to s is less than or equal to half. And how about in half is less than or equal to s is less than or equal to 1? It's going to be not just beta tilde of 2s minus 1, but we are going to add alpha tilde of 1 to that. Okay, so I'll just space that out a little bit since it got crowded. 0 is less than or equal to 1. So I'll write down the formula. Beta of 2s minus 1. This is what it would be if you had a star. But I want to begin where the previous curve ended, which is alpha tilde of 1. Okay. So 0 is less than or equal to half is not 0. Half is less than or equal to s is less than or equal to 1. Okay. Now, so observe. Eta tilde is continuous. I'm saying this because the definition without translation would not be, and p composed with eta tilde equals alpha star beta, and we also have eta tilde of 0 is going to be 0. Okay, because this eta tilde of 0 is just alpha tilde of 0. So this is a path which begins. So thus eta tilde is alpha star beta tilde. So alpha star beta tilde, remember, is the unique lift with those properties. Eta tilde is a lift, so it is this. Therefore, if I look at phi of the class alpha star beta, that class is going to be, which by definition this is just alpha star beta, it's the induced operation on fundamental group, is going to be eta tilde of 1. And eta tilde of 1, as you plug it in, is going to be alpha tilde of 1 plus beta tilde of 1. Okay. Literally they came in the other order, but in non-abelian fundamental groups one has to be careful about this. But in this case, let's just interchange them, and this is of course phi of alpha plus phi of beta. Okay. And general group theory will tell you the other properties of homomorphisms, like taking identity to the identity and inverse to inverse, will follow from these, but otherwise you can prove them directly as exercises using very similar arguments. You construct lifts and so on. Okay, so this has taken us most of the way. Now we have a relatively easy task of proving injectivity and surjectivity.